Discover a community of people who are curious about our world and proud of Wisconsin ideas. Discover the Wisconsin Academy of Sciences, Arts, and Letters. Since 1870, the Wisconsin Academy has been a place where people can connect with experts and learn from each other. Our public programs celebrate creativity and achievement, amplify ideas that inform and empower, elevate our capacity to thrive, affirm the values of the sciences, arts, and letters. We want to be your place to celebrate, connect, and learn. Join us and share our vision for a brighter future inspired by Wisconsin ideas. The Wisconsin Academy of Sciences, Arts, and Letters. Ideas that move the world forward.
Welcome, everyone, to the Wisconsin Academy of Sciences, Arts, and Letters. My name is Saliana. I'm the Events and Communications Manager here. When we do webinars at the Academy, we like to give visual descriptors to offer more of an auditory experience for people who might have trouble seeing, or just if you're just listening in with no video. So I'm sitting here in my home office in Madison, Wisconsin. I'm wearing a black and white jacket and floral shirt and some bright orange earrings. It's a lovely, clear fall day outside my window in front of me, and I think it's going to be a great night for stargazing. So I hope this talk tonight inspires you. Tonight, we're so excited to get to this very timely talk about the James Webb Space Telescope with astronomer Dr. Michael Maseda. We'll have an opportunity for Q&A at the end, and you're welcome to submit questions for that Q&A at any time in the chat or in the Q&A box. And you can find both of those at the bottom of your Zoom screen here. Before we get to Dr. Maseda's exciting talk, I'd like to just take a moment for a land acknowledgement to honor the Indigenous past and present of our current place here on Earth. The Madison office of the Wisconsin Academy of Sciences, Arts, and Letters occupies ancestral Ho-Chunk land, a place their nation knows as Dejop, which translates to 4 lakes. We recognize and respect the sovereignty of the Ho-Chunk Nation, as well as the 11 other First Nations who are caretakers and stewards of the place we now call Wisconsin. I'd also like to add, in keeping with tonight's talk theme, that tribal nations people share the impulse of people all over the world to look up at the stars, and thus tribal nations have their own traditions and stories associated with the sky that are also valuable to learn about. If you're interested in learning about Ho-Chunk sky stories and traditional beliefs about celestial beings, I recommend a helpful online collection which contains many of the Ho-Chunk people's celestial stories, and particularly this page, which I'm linking to now in the chat, which discusses generally Ho-Chunk beliefs about celestial spirits. And I found it quite interesting, and I hope you might as well. And with that, I'd like to introduce the Wisconsin Academy's Executive Director, Erica Monroe-Kane, to introduce our speaker.
Good evening. It's a pleasure for me to be here with you tonight. As Sally said, my name is Erica, and I am coming to you from the Wisconsin Academy offices in Madison. I have fuzzed out my background to reduce distraction. I am wearing a prominent pair of glasses and a bright red lipstick. I'm really excited about the talk this evening, and I'm so glad that so many of you could join us. As you saw from the video, the Academy mission is to create a better world by connecting Wisconsin people and ideas. Tonight's program is one example of how we bring curious minds together to learn and build understanding. We amplify the academic, creative, interesting, and inspiring people and ideas of Wisconsin through Academy talks, such as the one we're holding this evening, conferences, including the upcoming Climate Fast Forward Conference in October, exhibitions at the James Wattros Gallery, such as the works that are on view right now by Dakota Mace and Kyung A. Cho, as well as through our magazine, The Wisconsin People and Ideas. This particular magazine is a benefit that can be received by those who join the Academy as members. The Wisconsin Academy is an independent, nonprofit organization made possible through individual contributions and memberships. I invite and welcome you to support the Academy by becoming a member or making a financial contribution. I'm proud to be a part of a nonpartisan organization creating opportunities for civil discourse and building connectedness and understanding through programs such as the one we're holding this evening. It's my pleasure to introduce Dr. Maseda. Dr. Michael Maseda is an assistant professor in the Department of Astronomy here at the UW-Madison, and his research focuses on the growth and evolution of galaxies, particularly at early cosmic times. He uses observational data from large telescopes to characterize the physical processes happening inside galaxies, which will be pushed further with the advent of the James Webb Space Telescope. Welcome, Dr. Maseda.
Thank you, Erica. I will pull up my presentation. While I'm doing that, I'll just say that I'm here in my office on campus, UW-Madison. The sun is rapidly setting behind me, but over my shoulder, there's still a very nice view of Bascom Hall. I'm wearing a bright blue shirt, sky blue, perhaps a little bit in honor of the beautiful day that we've had today and the beautiful evening that I think we're going to be having, as was said before, potentially perfect for stargazing. But more than anything, I want to talk about astronomy from space, so not from telescopes on the ground, and particularly the really, really exciting time that we're in now, because we have a new telescope called the James Webb Space Telescope, or JWST, which is already producing phenomenally interesting and important scientific results, and it's only going to continue to produce more of those results as we move forward. And so it's not a small step, it's actually quite a huge one in terms of our capabilities to understand the universe around us. And so I don't think it's really an exaggeration to say that we're entering a new era of astronomy with the James Webb Space Telescope. Now, what you see here in the background was one of the original images that was released back in July from a field called SMACS 07224, sort of a long name, but almost everything that you see in this image, all of these points of light, are actually galaxies. So our galaxy is called the Milky Way. It's a collection of a few 100 billion stars, many of them like our sun. And our Milky Way is one of billions and billions of other galaxies in the universe. And many of these galaxies, which you can see here in this image, are very similar to our own, but very, very distant. So we're going to walk through over the course of this talk, images like this, what we can learn from them, how we learn about the universe. But I want to highlight already the gain that we're getting with JWST compared to other telescopes we've had in the past, most notably the Hubble Space Telescope, which many of you are probably familiar with. So if I show you the same part of the sky on the left with JWST and on the right with Hubble, you already get the impression that the JWST image is really much, much better. It's much crisper, it's much sharper. There's a lot more depth in the image. There's a lot more contrast. You can see more things. And that's not to say that Hubble is a bad telescope or that we can't learn anything with it, far from it. But JWST really represents a very, very large advance in capabilities compared to what we've had before. So what I want to do tonight is start outlining a little bit about light and some of the physics of light and concepts that are really important when we're talking about the distant universe. So things like redshift, and in particular, the need for observing, taking images in the infrared. I'll talk quite a bit about what infrared light actually is. I'll then introduce the James Webb Space Telescope, why it is the way it is, why it's such an important milestone in our understanding of the universe. And what I'm also going to do is walk through the first 5 images that were released back in July. Those public images are really great for highlighting the major science cases for the telescope. And importantly, I want to give you all the tools to understand them and give you the tools to understand any new discoveries and new images that might be coming out over the next few years, right? So you can fully sort of kind of follow along with the science as it comes in. And I'll talk a little bit about some of the prospects that we can expect over the next decade, but really, I think things are going to be progressing so quickly that it's difficult to say what kinds of science questions we'll be answering with JWST 10 years from now, right? We can't possibly even necessarily dream of those sorts of things. So it's really, really exciting for us. Now we have to start with a little bit of physics, but I promise I'm not going to have any equations. I'll try to keep things very qualitative. And I want to start by talking about light. So if you've ever seen a rainbow, or if you've seen, for example, white light passing through a prism being dispersed into the colors of the rainbow, you're actually seeing physics in action. So white light is actually made up of all of the individual colors of the rainbow. And what the prism is doing, or droplets of water in the atmosphere that actually cause rainbows that we can observe, all that is doing is separating light out into different wavelength components. So our eyes actually interpret different wavelengths of light as different colors. So every single color has a unique wavelength, going from the longest wavelengths, which are red, to the shortest wavelengths, which are violet, right? So we interpret these wavelengths as different colors. Now, That's just what our eyes can see. That's not all of the light that exists. So a star like our sun, for example, most of its light actually goes and is emitted in this wavelength range, somewhere between red and violet. But it has some light at longer wavelengths, which are called infrared, and it has some light at shorter wavelengths, which is called ultraviolet. So even though, for example, you can't see ultraviolet light, if you've ever had a sunburn, you can probably figure out that the sun still emits some ultraviolet light. Now, there's plenty of different wavelengths that we can't see. In fact, we can only see a very, very small range in terms of wavelengths of light. So the entire spectrum of light, which is what we call the electromagnetic spectrum, goes from radio at the very, very long wavelengths to gamma rays at the very, very short wavelengths, right? So in terms of decreasing wavelength, we have radio waves, microwaves, the infrared, and this very, very small range that our eyes are sensitive to, which we call visible light or optical. Then we have ultraviolet, X-rays, and gamma rays. And I think intuitively, when we talk particularly about ultraviolet, X-ray, gamma ray, those sound dangerous. And basically, when the wavelengths get very, very short, the energy increases. So they actually do have a lot of energy, and they are potentially very dangerous. Now, when you take a picture with a camera, we're used to interpreting the colors that we see in that image. But you can actually take images in any of these different wavelength ranges. So for example, I think the most intuitive one to think about is X-rays. We're used to seeing X-ray pictures of our bones, for example, and all that is showing you the different density of tissue that X-rays are passing through at different speeds. So we can take pictures at any of these other wavelengths. And I want to focus on the infrared a little bit. And if you've ever seen a thermal image or a heat image, like the one I'm showing you here of a cat, that's actually an infrared picture. So what this picture is showing, this picture of a cat, where the warmer parts of the cat, like the face and the ears, are represented by these lighter colors, the sort of yellows and whites, and the things that are cooler, like the tail, are sort of the more blues and the purples. So essentially, the color that you see in this image is really just encapsulating the temperature or the intensity of the infrared light. Okay, so infrared, temperature, thermal, these are concepts that you can start to relate for the purposes of this talk. But the colors that I'm using here, right, the oranges, the yellows, the purples, is completely arbitrary. So our eyes can't see this light. So in order for us to be able to see the image, we have to make colors. So we have to, as we say, give it some false colors. So I can equally turn the image in black and white, where I show that the brightest colors, right, the whitest colors are the hottest, and the coldest temperatures are the darkest. But it encapsulates the exact same information. Okay, so keep this in mind when we talk about pictures in the infrared with James Webb. The colors aren't necessarily what you could see because you can't see this light. So we've had to make choices, and we make representative choices about which colors to use. Now, one of the really great things about looking in the infrared, in addition to its thermal imaging properties, is that in some cases, infrared light can actually pass through smoke and fog and clouds. So on the left here, there's a picture of a foggy day. You really can't see very far because the fog basically just obstructs the light. But if you look at the same image in the infrared, in this particular case, you can see that there's a person on the other side of this pond. So this infrared light has no problem passing through these clouds. So it's another very important point when we're talking about imaging with JWST, which I'll come back to in a little bit. There's an important physical concept that I want to introduce with light. And I think it's actually more intuitive to think about in the context of another wave, which is sound, right? So our ears interpret different wavelengths of sound as different pitches. So higher pitches are going to be lower, going to be shorter wavelengths. Lower pitches are longer wavelengths. So the physical effect that I'm referring to is called the Doppler effect. And you're familiar with it if you ever have seen a fire truck, for example, with a siren that's moving. So when the fire truck is driving towards you, essentially the sound waves from the siren become compressed. So they get pushed to shorter and shorter wavelengths, which we interpret as a higher pitch. As soon as it passes us, the wavelengths get stretched out longer and longer, which we interpret as a lower pitch. Okay, so moving objects that are emitting sound, the Doppler effect is saying, depending on whether it's moving towards us or away from us, the sound pitch will change. Now, the same effect can happen with light, right? But something has to be traveling much, much faster than a fire truck in order for this to happen. And that's simply because light travels at a very, very, very high speed. When an object is emitting light and it's moving very, very rapidly towards us, the wavelengths get shorter. They get compressed, pushed to shorter and shorter wavelengths, and that can be interpreted as bluer colors. On the other hand, if they're moving away from us very, very quickly, the waves get stretched out to longer wavelengths and they get more red. And that's what we interpret as redshift. So objects that are rapidly moving away from us, we expect the light from them will be emitted at longer and longer wavelengths, particularly into the infrared. And that's called redshift. Now, the reason why this is important is because the universe is a big place and the universe is expanding, right? So in the 1920s, people like Edwin Hubble and Georges Lemaitre understood essentially the way that the universe worked. So they understood that our sun is one of a few 100 billion stars in our Milky Way galaxy. The image that I'm showing you here is an artist's impression because we live inside it, so we can't actually see what it looks like from the outside, but our sun is about 2/3 of the way out. The galaxy is shaped a little bit like a disk or like a pancake, pretty flat, and so we're living inside that disk. Our galaxy is one of many in the universe, right? Hundreds of billions, trillions of galaxies in the universe. And we started with an initial Big Bang. So the universe, everything in the universe was all in one place at some very, very early time, and then it exploded. And we don't know actually all of the details about how the Big Bang actually worked, but the upshot of it is that the universe is expanding. So everything was in one place, the Big Bang happened, and ever since then, everything has been moving away from each other. So after the Big Bang, the first stars started to form inside the first galaxies, but all of the galaxies are going to be moving away from each other. So you can visualize this if you think about a balloon. And let's say that you paste little pictures of galaxies on the outside of this balloon. Now, as you inflate the balloon, every single one of those galaxies is going to view every single other galaxy as moving away from it. So there's no one galaxy in the middle, so to speak. Every galaxy views all of the other ones moving away from it. And because it's the space itself that's expanding, or in this analogy, the sort of surface of the balloon that's expanding, the further away a galaxy is from you, the faster it's going to be moving away from you. Right? So the more distant an object is from us, the more its light is going to be redshifted. And also because light travels at a fixed speed, there's a fixed velocity to it that it takes a long time to reach us from distant objects. So the more distant an object is from us, the further back in time we're actually able to see. And so this is really important when we're talking about understanding what the early universe looked like, what the first galaxies looked like. We need the ability to look really, really far away, the most distant galaxies, and those galaxies are going to be the most redshifted. Now, when we actually take pictures in astronomy, we don't really take color pictures in the same way that you would take with your camera. So I show you here this inset panel on the right with a color image of a galaxy, but we don't actually take that as the picture. Instead, what we do is we have filters. So we isolate certain colors, right, certain wavelength ranges, and just take a picture of the light at that wavelength. And then afterwards, we can combine all of those images together into one color composite image. So that image of this galaxy is actually made up of these 7 individual components and each of these individual colors. Now, we do that really for 2 reasons. The first reason, as you can see from these different color images, is that the galaxy looks different in all of them. And so in particular, in the ultraviolet or in the blue, you see the galaxy, really just the rim of it is lighting up. And that's actually because when we have stars being born, there are a few stars that don't live for very long, and they emit a lot of blue light and a lot of ultraviolet light. And so when we see that, we know that stars are really just in the process of being born. And so we could see that in this case, they're forming on that outside rim, whereas the center of the galaxy, if you're looking in the sort of orange and the red colors, the center of the galaxy is a little bit more diffuse and kind of glowing in a little bit of a different way. And so that's because the stars in the middle of this galaxy are a little bit older, and those older stars emit more red light. And there's also quite a bit of gas and dust in this galaxy, which also emits light in these colors as well. So what we've done is essentially, with all of these different color images of the galaxy, we started to dissect it, right? We've learned about where, for example, it's forming stars, where its old stars are. And so we're actually able to learn a lot more about the physical properties of the galaxy and how it kind of came to be the way that it is. The second major reason that we would do something like this, where we have these individual images, comes when we're talking about studying very, very distant galaxies. So this particular galaxy, given that it's very sharp and very well resolved, is actually very close to us. And so it's not significantly redshifted. But if this galaxy were further away from us, all the light that we see, for example, as blue would start to come out in green, and the green light would come out in yellow, and the yellow would come out in orange. And if we're even further away, you can imagine the blue light would come out in the orange. And if it were extremely far away, talking about the very, very early universe, you would expect that essentially all of the light would be coming out at very, very long wavelengths, sort of in the infrared. Because as I said before, stars like our sun, generally speaking, emit most of their light within the spectral range that our eyes are capable of seeing. So as soon as it gets far enough away that that light is redshifted, you would expect to not see anything for a galaxy in blue, yellow, green, and you would only see it at the longest wavelengths. And in particular, the Hubble Space Telescope, which I have this picture of on the left, really can't observe very far into the infrared. And so we've been able to see galaxies like this, potentially very, very far away, so very early into the history of the universe, but there's just a finite limit into what we do because we can't see further into the infrared. So we need something to push a little bit further. And this technique where we have these pictures and all of these different imaging wavelength ranges is how we differentiate between something that's small because it's far away versus something that's small just because it's small and nearby, right? So for a local galaxy that is just inherently very small, you'd still see some green light, some blue light, for example, whereas the most distant ones, you'd only see light at the longest wavelengths you can see. So we have this motivation. If we want to find galaxies at the very beginning of the universe, we need to look at longer wavelengths. We need to look in the infrared to be able to find them and study them. Now, on much, much smaller scales, right? Now we're talking certainly well within our Milky Way galaxy, we can take pictures of regions where stars are being born. And I think this is one of the most iconic images from Hubble. These are called the pillars of creation, which are these giant clouds and columns of gas and dust. And essentially, we know that stars are being born inside there. So stars are formed out of clouds of gas and dust that, because of gravity, it compressed slowly, slowly, slowly to the point where everything gets hot enough that it ignites and starts to glow. The problem is, once this process happens, right, once the star is actually born and starts to emit light, it's still inside a cloud of gas. And so you can see on the sort of edges of these fingers or these columns, little streaks of light coming out, right? So that's a little bit of light from these newborn stars peeking out, but for the next few thousand or potentially even millions of years, we won't be able to see them because they're encapsulated inside the gas. But as I said, infrared light in some cases can peer through gas and through dust. And so with an infrared picture, we might be able to see inside and see inside these stellar nurseries and see the stars actually being born, which is important, right, to understand how stars are born, but also important to see how planets around stars are born, because otherwise the clouds are completely blocking our view. So from the very, very distant universe to the very nearby universe, there was a push to have infrared capabilities on a telescope. And that's exactly why for the better part of the last 2 decades, NASA, the European Space Agency, and the Canadian Space Agency, in addition to numerous aerospace corporations, have been working hard on a telescope to solve these problems. And that telescope is the James Webb Space Telescope, or JWST. Now, it has capabilities that are actually very, very different to Hubble's. And so, we often refer to it as the successor to Hubble, but it's really a complement to Hubble because it does things that Hubble can't do, and Hubble can do some things that JWST can't do either. JWST is a huge step forward compared to any other infrared telescope that we've had before. Usually these telescopes are in space because observing in the infrared is very hard to do from the ground because everything is warm and we have the Earth's atmosphere to deal with. But it's about a factor of 100 times more sensitive than any telescope in the infrared that we've had before. And it's big. Right? The mirror is about 3 times the size of Hubble's, which is sort of 21 feet across. And that's really, really important when we're talking about taking really sharp pictures, right? So the larger the mirror you have, the sharper the pictures you can get. But also it's really important when we're talking about taking pictures of things that are very, very faint. So we essentially can collect more light from faint things if our mirror is larger. JWST was built to have a very, very large mirror. Now, it was launched successfully by the European Space Agency from their facility in South America in December of last year. And what I'm showing you here is the last picture that we have of JWST. So this is the bottom part of the telescope as it was ejected from the rocket after it was launched into space, and as it was making its journey to its final position, which I'll get to in a minute. Now, this is just a cartoon illustrating the relative size difference between JWST's mirror, Hubble's mirror, and a person. So Hubble's mirror is a bit bigger than a person is. JWST's mirror is 3 times larger. And it's also shaped very different, right? It's sort of hexagonal and made up of these individual segments, which is also a very important part of its design, which I'll get to in a minute. When we talk about Hubble and Webb, as I said, Webb is a real complement because Hubble, for the most part, is sensitive to the same light that our eyes are in that visible regime, with some capabilities in the ultraviolet and some capabilities in the infrared. But JWST really was designed to be sensitive to infrared light. Now, what that means is that it actually can't observe very much light that our eyes can observe. It can really only observe down to sort of yellow or orange. So there's a very narrow range in which JWST and Hubble can actually observe the same light. Right? JWST much more focused on the infrared. Now, what I'm showing you here is an image very similar to the one that I showed at the very, very beginning, which is one of these fields where basically everything that you see is a distant galaxy. And just comparing the quality of the image that you get from Hubble, which are on the top panels, to JWST on the bottom panels. And I think it's more evident when you zoom in. So I'm zooming in on those right panels here. And this is a galaxy that's actually a lot like our Milky Way. So it's shaped kind of like a disk, and it's inclined so it's face on to us, so we can see the full extent of the disk. And what you see in the Hubble image is a little bit blurry. Maybe the galaxy just is kind of fuzzy, but when you have the higher angular resolution of JWST, you can actually see the sort of pinwheel structure quite a bit easier. And you can also see that the galaxy has these really bright blue kind of knots in it. And that's actually, as I showed you before, where stars are being born. So we can see that stars are being born in a couple of really densely populated regions inside this galaxy, right? They're not forming everywhere. Now, for me, I think actually the most exciting thing is in the background of this image, right? The background of the Hubble image, you could see a couple of little dots, but not very much else. And the JWST image, this image is full, essentially. There are a lot of these points of light, and those are all galaxies. Now, I'm highlighting just a few of them here. The ones that I have circled in green are things that technically Hubble could have seen, but they're actually just too faint. So these galaxies are basically just not big enough. They don't have enough stars that aren't emitting enough light for a telescope like Hubble to actually detect. And the ones that I have circled in red are really the most exciting because those galaxies are just too distant, right? Their light is redshifted too much for Hubble to be able to see them at all, and yet they show up very prominently in our JWST images. Now, we have had other infrared space telescopes before, for various reasons. I'm not going to say anything bad about these telescopes, but in terms of the quality of the images, they really can't deliver anything like JWST. So moving from the left to the right here, this is the same part of the sky. We have the WISE telescope, which has a 16-inch mirror. We have the Spitzer telescope, which is 2.8 feet. And then we have JWST with its 21-foot mirror. And so these points of light get sharper and sharper. And actually on the right image with JWST, they kind of look like snowflakes or stars. And actually that's a sort of telltale sign that what you're looking at actually is a star in our galaxy. So just because of the optics of the system, stars are actually very, very compact points of light. And so the system actually kind of optically makes them diffract like this. So if you ever see this kind of snowflake shape, you know that you're looking at a star in a Milky Way galaxy, as opposed to a galaxy that's, even if it's very small, won't really show up like this. So we see that those blurs that you see in WISE are actually stars. And also very interestingly, as you get to the higher and higher sensitivity and higher resolution, you start to see what look like clouds. And we're observing from space. So these are not clouds in our atmosphere. These are actually massive clouds of dust in the Milky Way galaxy. Now, I said infrared light is actually kind of like thermal radiation. And so this is actually dust that's a little bit warm, right? By the standards of Earth, it's very cold, several hundred degrees below zero, but it's emitting just enough heat that JWST is able to see it. So we could see these clouds of dust exist. Now, when we talk about heat sensitivity, thermal radiation, just to highlight the real incredible power of JWST, if JWST were on Earth, and it were able to observe in the infrared in the same way that it can from space, which it can't do, right? Because the Earth is very warm. Nevertheless, it has the sensitivity that it would be able to detect the heat signature of a bumblebee on the moon. Right? That's really incredibly faint signature, and yet JWST can handle that actually quite well. Now, it doesn't look like a telescope. It has this hexagonal mirror. There's this big sort of apron on the bottom. If you squint at the Hubble telescope, for example, it's shaped like a tube, and that makes sense for a telescope. Light comes in one side, and you have your cameras on the other. But everything about JWST is really optimized, as I said, to be an infrared space telescope, which has motivated a lot of the design choices. And the first choice is where to put it. And it's at a point in space called L2, or the second Lagrangian point, which is 1 million miles from Earth. So it's actually orbiting around the sun once per year, just 1 million miles further out than Earth. And L2 is a really interesting place because the gravitational pull from the sun, from the Earth, are actually about the same. So it's relatively easy to kind of stay put there, orbiting around the sun. And actually, really importantly, because of this, the sun and the Earth are always in one direction from the telescope. So what that means is you can block all of the light and all of the heat from the sun, right, which is really bad when we're talking about infrared observations. You can block all of that out, and you can put your telescope antenna to beam the data back to Earth always in the same direction. Right? So you're always going to have a dark, very cold environment to observe in, and you don't have to move your telescope a lot whenever you need to beam the data back. Now, Hubble, on the other hand, is orbiting just a few hundred miles above the Earth's surface. And so what that means is every sort of 90 minutes, it's rotating around the Earth. Now, that's really good for some reasons, right? So if it ever broke, which it did, or if it ever needed to be upgraded, which it did, astronauts could go up and do that. Right? JWST is too far away for that to happen. So we really get one shot at making this work. But on the other hand, right, you get the advantages of being at L2, where it's very dark and very cold, but also Hubble has to deal with the Earth kind of getting in the way every 90 minutes. And so if you're observing something and you need to observe for a very long time, you have to kind of get interrupted in your cycle because of the Earth. With JWST, that doesn't happen. So you have a lot more flexibility in terms of what you can observe and when. Now, that weird apron thing, as I'm showing you in this image here, is actually what we call the sun shield. And it's this sort of membrane, actually made up of 5 different layers, that's the size of a tennis court. So each of these 5 layers is made of a material called kapton, and the whole idea is that this can sort of passively block out all of the light and the heat from the sun. So we have one side of the telescope that's facing the sun. That's the sort of bottom of the sun shield, and it's actually quite warm there. It's about 128 degrees, and that's warm enough that you have a lot of thermal radiation, which would interfere with your ability to take good infrared pictures, right? For the same reason that you don't have an optical telescope that you use during the day, because the sun is so much brighter than what you want to observe, you want your telescope in the infrared to be as cold as possible. So those 5 layers of material progressively dissipate more and more of the heat. So you go from that 128-degree warm side of the telescope to the cold side of the telescope, which is 383 degrees below zero, right? So it's significantly colder, right? That's really perfect for infrared observations. And the system is completely passive, right? So there's no fuel, there's no refrigeration that's required in order to get the telescope this cold, right? So that's really important in terms of the longevity of the mission. Now, the mirror is actually made up of 18 hexagonal segments that all fit together into one larger hexagonal mirror. Now, those segments are all identical, and they're all made of a material called beryllium. It's an element called beryllium. And on the left-hand side here, you see the back plane of one of the mirrors, which is this sort of, honeycomb structure. And the whole idea with anything that launches into space is you want it to be very lightweight. So having this honeycomb and having it made out of beryllium is very lightweight, but also very importantly, beryllium doesn't warp or change shape when the temperature changes. So as you go from being warm to, as the telescope was cooling down, to 383 degrees below zero, right? Nothing warped, the mirrors didn't crack. It was very, very important that the mirrors didn't crack. Now, beryllium naturally is kind of silver in color, but the last thing that was done after the mirrors were polished was they were coated with a very, very thin layer of gold. In fact, there's only a couple of ounces of gold on the entire telescope, but gold is really, really good at reflecting infrared light. So ideally, your mirrors are going to reflect all of the light that comes onto them, and gold is really good at reflecting infrared light. It's not just because it looks cool, but it also looks cool. Now, big mirror, right, 21 feet across, tennis court-sized sun shield, that's just too big to fit in any rocket that we have, right? Even the European Space Agency's largest rocket, which is the Ariane 5, can't fit anything that large. So the whole thing needed to fold up into a package that's about 35 by 15 feet. And that's one of the motivations for those hexagonal segments on the mirror. So actually the outer segments can kind of fold back like ears, and the entire sun shield also needs to be packed and folded up into this compact shape. So I have some pictures here showing you after the telescope was fully assembled, it was folded up, kind of squished all together and tucked into the nose cone of the rocket right before launch. Now, all of that, of course, also meant that everything had to unfold, and everything had to unfold in space, and everything had to work. There was no ability for us to go up and fix it if anything got caught or got stuck. and there were a lot of moving parts. So in the 2 weeks that it took for everything to unfold, we didn't have images, it was really just telemetry, and it was incredibly stressful and nerve-wracking, right? Just basically getting information, deployment 1 worked, deployment 2 worked, but everything worked flawlessly, right? This is far and away the most complicated scientific mission in space, and everything worked extremely well, which is really a testament to the efforts, as I said, of many thousands of people in many, many different organizations around the world. So we have now a fully operational, fully functioning observatory. So when we're talking about the science, right, what are we going to see with that? There are actually 4 main science areas of JWST, and those are actually all covered by the images that I'm about to show you. The first theme, as I kind of touched on before, how are stars formed? And how are planets around those stars formed, right? We can't really, up until now, observe this directly. So how common is it for stars like our sun to have planets that are rocky, orbiting around the place that our Earth is, for example, where we know that there could be liquid water on the surfaces? We just need more demographic information about planets and planetary systems and how they're formed around their host stars. Going beyond that as well, and touching on life, how many planets could potentially host life, have liquid water on their surfaces, have atmospheres with oxygen and nitrogen in them, right? We really just, at this time, don't have a lot of information, in particular about the types of planets that could host life as we know it. On much larger scales now, right? So everything with stars and planets and life, we're talking about well inside our Milky Way. But our Milky Way is one galaxy amongst many hundreds, if not more, of billions of galaxies in the universe. And galaxies, for the most part, are actually pretty similar, even though they might contain from a few thousand to a few hundred billion stars. Many of their properties are actually very similar to each other. So how did that come to be, right? How did this fairly complicated system of stars end up being relatively self-similar? And how did that change over time, right? What did a galaxy like our Milky Way look like, for example, at the time when our sun and our Earth were formed? We don't really know that. And then moving back to the most extreme times, the very earliest stages of the universe, immediately after the Big Bang, the universe was dark. There were no sources of light. It was only after some time, and we don't know exactly when, only after some time that the first stars began to form inside the first galaxies. And we have what we call, kind of poetically, the end of the dark ages, right? When did that happen? What were those stars like? What were those galaxies like? And then going back into the previous point, how did they become like the galaxies that we see around us today? So those are the 4 major themes of JWST, and all of them are covered in the images that we're about to go through. So the first image, this is something called the Carina Nebula, and this is an image that I think really highlights the wonderful sort of textures that you can see in these images. So this is a region of gas in our Milky Way galaxy that's a stellar nursery. So stars are actively being born in this kind of like rippling, kind of brownish cloud of gas. Now, compared to Hubble, which you could see here on this left panel versus JWST on the right, you can already start to see kind of through the haze a little bit more. As I said, clouds of gas and dust kind of prevent optical light, like Hubble is sensitive to, from going through. With JWST, we can start to see through that haze and see through that fog. And so the picture is much sharper, and we can also see anything inside those clouds are stars that are actually being born inside those regions. Now, the reason why there's this kind of interface where the top part of the image is relatively clean and the bottom part of the image is full of these sort of clouds is because actually just off screen, just to the top, there were a few stars that formed probably a few million years or a few 100,000 years earlier, and they've already started to kind of blow their winds and eject all of the gas that was around them. So they've started to clean out the area around them, and they're pushing this gas downwards. And so if we were to look at this region again in a few sort of 100,000 years or so, we wouldn't see any of these gas clouds anymore. You only see this when stars are just being born. So we don't see big clouds of gas around our sun. That's because our sun formed several billion years ago, and it's already cleared out this region, right? So you see this interface between new stars being born and stars that were born just a little bit earlier. Now, as I said, with infrared light, you can actually start to see even further into the clouds. And so JWST can take other images at other wavelengths, for example, further in the infrared, and we can see even further inside this cloud. And that's in this region here. where you can see this overlaid, right? So this image isn't quite as colorful, but what we're seeing is deeper and deeper inside the cloud. And I want to highlight this region here where you actually see a bunch of stars that are actually born right next to each other. This is a really, really what we call a dense star forming region. And actually, we think this is relatively common. We think that stars are often born in pairs, for example, or binary systems. Now, stars are not just born, but stars eventually die. And so if you've ever heard someone say that we are all made of stars or we are all made of stardust, that's literally true. So when the universe formed, the only elements that existed were hydrogen and helium. So everything else, carbon, nitrogen, oxygen, iron, gold, everything was made inside stars. So stars fuse hydrogen and helium into heavier elements, and those elements get released when the stars die. So what this image is showing you, it's called the Southern Ring Nebula. This is a star that's in the process of dying. So it has been dying for quite some time, and it's been kind of ejecting material. So there's these sort of concentric shells coming off it. You can see the sort of clouds and material coming off of it. And this is all material that's been enriched. And when we say enriched, meaning the star has taken hydrogen and helium and made other things. And so this has been over time released out inside to the galaxy. Now, this is cool in and of itself, but actually one of the really interesting things with this particular system comes when you look even further in the infrared, like I showed you before. And if you look at longer wavelengths, all of a sudden you can see a second star in there. So as I said before, many stars we think are actually born in pairs. So if you've ever actually seen Star Wars and the planet Tatooine with the two suns, that's actually a thing that can happen, right? Stars can exist in binaries, and those binary systems can have planets. But in any case, what you can see here is that that star, we otherwise couldn't be able to see it because it's surrounded by all the gas and the debris coming off from the dying one. But that star is still alive. So one of the stars is living and one of the stars is about to die. I think that's a really, really exciting thing. And otherwise, it was completely invisible simply because of all the material being ejected. Now, what I'm going to show you here is talking about planets, and I want to really caution you, the background image here is an artist's impression, right? I think it's maybe disappointing to think when we're talking about other planets, we're not going to see beautiful pictures of other planets. They're simply too small, but we can get really exciting scientific information about them. Now, this is a system that we call WASP-96b, and the plot that I'm showing you here is actually monitoring the star's brightness. So one way of finding planets is monitoring the brightness of stars and seeing essentially how the brightness changes over time. So generally speaking, a star like our sun has about the same brightness over time. If you look at it tomorrow versus the next day, it's going to be the same brightness. But if you're looking at another star, maybe very far away, depending on the alignment, if it has a planet orbiting around it, and that planet comes between that star and us, that planet is actually going to block out some of the light. So if you monitor the light brightness, for example, as a function of time, you would expect to see, if you have planets, little dips. And depending on the frequency of those dips, you can figure out, for example, how often the planet is orbiting, so how quickly it's orbiting, and also how big the planet is. And in this particular case, right, so this is what we call a light curve. This is a planet that's actually about the size of Jupiter, but it's orbiting around its host star, which is a star very similar to our sun. It's orbiting around that every sort of 3.5 days. So that means this Jupiter-sized planet is orbiting well within where Mercury's orbit around our sun is. And that means that this planet is really, really hot. It's about 1,000 degrees. So by no means am I going to imply that there's going to be life on this planet, but one of the great things that we can do now with JWST is take a spectrum of that planet. So what a spectrum is when you actually take pictures of the galaxy at very, very small wavelength ranges. So if you're just very, very specific colors, and you do this, you don't get a beautiful picture, but what you get is a sort of graph. And this graph is showing you the amount of light coming through the atmosphere of that planet as a function of the wavelength or the color of that light. Now, the technical details of this maybe don't matter so much, but essentially individual elements or molecules have very distinctive signatures in the spectrum. And so in particular, something like water has a very, very characteristic pattern where it emits and absorbs light slightly differently at different wavelengths. And so what we see in the spectrum here is that this planet, it's the size of Jupiter, orbiting super close to its star, actually has water vapor in its atmosphere. Right, so spectra are actually our way of kind of taking fingerprints of planets. And we're going to be able to, with JWST, look at other planets, maybe planets that are a little bit more reasonable to assume could have life, right? Not necessarily really hot Jupiter planets, but we're going to be able to study a lot more about the atmospheric characteristics of planets around other stars in our Milky Way galaxy. Now, moving to much, much larger scales here, right? We're talking about galaxies again. This is an image called Stephan's Quintet. And this is 5 galaxies that are much, much larger than all the galaxies you see in the background. And that's because they're all relatively nearby. And actually 4 of the 5 that you see on the right-hand side of the image are actually very, very close together as well in space. And so what's actually happening is these galaxies, the gravitational pull of these galaxies, is making them run into each other. So individually, these galaxies, were living their own lives for billions of years. And as they got closer and closer to these other galaxies that were nearby, eventually gravity is going to throw them together. And the stars, for example, that were orbiting inside those galaxies are going to be disrupted on their orbits. And this very violent process, which takes millions or billions of years to complete, is eventually going to make a completely new galaxy. So a new galaxy can be formed when 2 or more galaxies run into each other. Now, if you've ever been to the southern hemisphere and you've been outside at night, you might be able to see something that we call the Magellanic Clouds. So these are actually 2 very, very small galaxies that are running into our Milky Way. And you might be able to say that our Milky Way is kind of eating those galaxies. So that's a very small example of merging. And in a few billion years, our Milky Way is going to run into our nearest neighbor, which is the Andromeda Galaxy. And we're going to end up making a new galaxy out of that. Now, because this takes so long, right, we don't see any one galaxy sort of changing in this process over time. It's really important to study these kinds of systems to see how often it happens, see what the sort of end products are, to kind of fit in with the picture of how do galaxies evolve, right? How important are mergers? How important is the environment that a galaxy lives in determining its properties? So finally, I'm going to come to the last image, which was actually the first one that I showed, which is what we call a gravitational lensing cluster. Now, I'll go through the details of what that means, but other than maybe 1 or 2 sort of very bright stars that you see, which are in the foreground in our Milky Way galaxy, pretty much everything else you see in this image is a distant galaxy. Now, if you look a little bit closely, things might look a little bit weird to you. Some of these galaxies are actually stretched out, elongated, distorted. And that's actually something really, really interesting, which we call gravitational lensing. So if you're used to optics, if you're used to looking through magnifying glasses or any sort of curved pieces of glass, you know that light can be deflected. So what I'm showing you here is the stem of a wine glass on a piece of graph paper. And the lines of the graph paper, even though intrinsically they're straight, the glass is actually making them kind of bend around. Now you can deflect light from glass, and you can also deflect light because of gravity. So anything that has gravity can actually deflect light a little bit. And the more gravity you have, right, the heavier the system, the more you can bend light. So you can imagine a configuration where you have a very, very massive galaxy, let's say, and it's actually light coming from a source behind it towards us can get bent and distorted and diffracted and kind of shifted around. And that's exactly what we're looking at. So in this image here, those galaxies in the center, the kind of fuzzy white galaxies, are actually relatively nearby and very, very heavy. And everything that you see that's kind of distorted behind it, distorted around it, are actually behind it. So this galaxy, these galaxies in the center are acting like lenses. Now, one of the really interesting ways that we can use this to actually do science is the fact that we understand optics pretty well, right? We understand how light can get bent and diffracted because of large parcels of matter. Galaxies are made up of 2 things that are heavy. They're made up of stars, which we can see, and they're made up of dark matter, which we cannot see, right? But dark matter, even though it doesn't emit any light, has mass. So by carefully measuring the positions and the amount of sort of distortion in the background galaxies, we can get a constraint on how much mass there actually is in the galaxy that's acting like a lens. So we can actually determine how much dark matter is in a galaxy and where that dark matter is distributed by looking at fields like this, right? So that's really exciting. It's one of our only sort of observational ways of learning very much about how dark matter interacts with galaxies, or rather how galaxies have dark matter and how that dark matter is distributed. The other really interesting thing that happens with this is just like with a magnifying glass. In some cases, the galaxies that are bent and distorted are actually magnified. And so, for example, you could have cases where a galaxy is otherwise too faint for us to observe, but it gets magnified to the point where we can see it. So we like to say that this is our ability to point a telescope at one of nature's telescopes and see things that are even further away and even fainter. And in fact, what I'm going to show you here is just a couple of configurations of this, right, with a background galaxy. Galaxies don't move, right, but this is just showing you how this sort of lensing can actually work to magnify sources. Sometimes it looks brighter, sometimes it can actually kind of distort it, make it look like a ring or like an arc behind this foreground galaxy. Now that magnification is really, really exciting, right? Because what we can see, for example, you never would have picked it out in this image, but I have it zoomed in now. This little tiny blob is actually a galaxy that's extremely far away. In fact, that light has taken more than 13 billion years to reach us. And the universe is only about 14 billion years old. So with this gravitational lensing, we've already been able to see a galaxy within the first billion years of the universe. And much like what I showed you with that planet, we can take a spectrum of it. So we can determine what sort of elements are present in that galaxy. Now, this is really exciting because at the beginning of the universe, there was only hydrogen and helium. So every other element was produced inside stars. And the spectrum of this particular galaxy also shows, in addition to hydrogen and helium, shows oxygen and neon, which means that already less than 1 billion years after the Big Bang, this galaxy has already not only formed a lot of stars, but those stars have also, some of them have died. So this has had some generations of stars being born and dying already within the first 1 billion years of the universe. So these sort of fingerprints or barcodes are going to be really, really useful in understanding how stars formed in the universe, when they formed, and what the first galaxies were actually like. So what are we going to see, right, in sum, right? What are the things that we're expecting to see and hopefully have answers for moving forward, right? I think one of the big ones, and actually this was the original motivation for JWST more than 20 years ago, is what was the very, very early universe like? What were the first stars and the first galaxies like? When did they turn on, right? When was the first sources of light in the universe? We don't know. And JWST is going to give us a very definite answer to that very, very shortly. On smaller scales, right? Is our solar system unique, right? A planet like Earth around a star like our sun. How often does that happen, right? Is this a really, really rare occurrence, or is this something that's common? And I think building on that, right? Are there planets that have atmospheric characteristics that are necessary for life, having nitrogen and oxygen in their atmospheres in addition to water, right? I don't think we're going to be able to definitively prove that there is life on these other planets with JWST, but I think we're going to get a lot closer to understanding how unique those conditions actually are, right? So it's really, really an exciting time. I think, everything, if you talked to me 8 months ago, I would have been very, very stressed with the deployment and everything like that, but everything's up and running. We have a live observatory, and it's really, really, really exciting. I think the kinds of science that we're going to be doing 10 years from now isn't even necessarily the kind of things that we can be dreaming about doing now, right? Everything was successful. And I think I have to say, I played a very, very small role in all of this. I'm a scientist, I'm not an engineer, I didn't design the telescope. Many thousands of people around the world from different space agencies, aerospace corporations, and scientists have really kind of come together for this mission. We've all recognized exactly how important this is, and it's going to be really fun. So I want you all to stay curious. I hope you all have learned something. I hope I've given you some tools to understand and interpret new results as they come out. And yeah, stay curious. There's some links here for places for more information, but I really just hope that you are excited about James Webb in the same way that I am. Thank you.
Thank you, Dr. Maseda, for that talk. That was great. Folks, if you have questions, feel free to enter them in the Q&A below or just in the chat. I'll be logging those, and we'll be going through and answering questions as they come up. To start us out, I wanted to ask, I realized, Dr. Maseda, that you worked on a particular instrument on the James Webb Space Telescope.
Yes.
I wonder if you could say a little bit more about that instrument, and also maybe what are some of the other instruments that are at work on the telescope. I think people think of like telescopes like this as one thing, but it seems to me from talking with you that really this telescope is made up of many different parts that are doing different things.
Yes, that's right. So in particular, I think this last thing that I touched on is a good example of that. So the instrument that I worked on, and by worked on meaning I worked on some of the scientific planning of it, so not the sort of engineering development of it, was called NIRSpec, which is called the Near Infrared Spectrograph. And that's the bottom part of this panel, where we get the spectrum, for example, of galaxies or the spectrum of planets around other stars. And this is a really exciting instrument, but you have to know what you want to look at to use it. So you have to know, I want to look at this galaxy, or I want to look at this other galaxy in order to take the spectrum and determine what the chemical composition of a galaxy is. So that top image, right, the image that we showed you at the beginning that was used to select this galaxy in the first place was a second instrument called NIRCam, the near infrared camera. And that one was developed at the University of Arizona. And so there's this great partnership between the instruments. You know, we can use some to discover things, and we can use others to follow them up and learn more about them. So they're really all very complementary.
I'm sorry, muted myself to avoid any distracting sounds, but always bites you, that mute button. We had a question from the audience wondering what year the James Webb Space Telescope was first envisioned. First, there were several parts to this question, but we'll just maybe start with that part.
That's actually a very hard question to answer. So Hubble was launched in the very early 1990s. And even before Hubble was launched, there was already discussion about what to do next. So I think, depending on who you ask, the very first discussions and plans for what became JWST happened, I think, probably in 1988, 1989, around that point. But the main thing is missions that are this large and this complicated are rarely the brainchild of one person alone. And so there were many sort of competing designs. And I think over time, things were kind of honed in a little bit more. And it wasn't really until the late 1990s that JWST as we know it was envisioned. So it was a couple of different projects that kind of came together, you know, compromises in terms of just settling on what the major science goals were, what the design case was. And things really started to take shape late 1990s, early 2000s. And that's also when some of the construction and some of the contracts actually started.
Cool. We're getting lots of questions now and lots of praise as well of your presentation. People are finding it easy to understand, and it's such a complex topic. So thank you for being a good communicator about this telescope, which is so complex. And speaking of its complexity, another question was, what was the chance that this telescope would unfold perfectly after the launch? Was there, like, you know, what was the chance of failure?
That's a good question. I've asked, so much of the actual sort of deployment sequence, many of those mechanisms were actually designed by aerospace corporations, and many of them have trade secrets and things that they're not necessarily always willing to talk about. And I remember a few years ago, I was at a conference and I was speaking to someone who worked at Northrop Grumman, who was one of the major contractors, and I asked him this question. And what he told me was, I can't actually tell you. I can't tell you whether we've done anything like this or not, because they do a lot of defense work as well. But what he said was, this is certainly one of the most complicated things we've ever done, but we have a very, very good record of, you know, all of these individual deployments working, but they never put sort of everything together. So I think people were very confident going in. You know, I certainly think that there was a lot of redundancy built in, but also this was tested much, much, much more rigorously than anything we've had before. So you know, Hubble had a huge problem right after launch. You know, it was discovered that the mirror was basically the wrong shape, and so all the pictures were blurry. You know, you could send an astronaut up to fix Hubble, and that's what they did. They gave it glasses, as they say, but you couldn't do that with JWST. We knew we had one shot, and so the amount of testing, the years and years of testing that it went through were extremely rigorous. So I think, you know, as nervous as I was about it, I think it was very, very well tested, and it showed. Everything worked really flawlessly.
Thank you for that answer. A couple of questions have come up regarding the lifetime of JWST and vulnerability. Some people asking what's the expected lifetime of it, and others asking, you talked about some of the issues with Hubble orbiting the Earth, and sort of that JWST is further out, that mitigates some issues with like the Earth getting in the way. But is there any issues with like the telescope being hit by a comet, asteroid belts, like different things like that? How long is it meant to last, and what could potentially happen to it out there?
Yeah, so good questions. So it's actually not at a one fixed point, as you can see here in this image. It's actually orbiting around L2 slightly. So JWST is moving, in addition to moving around the sun, it's moving around this one position in space, which orbits around the sun once per year. So JWST does require a little bit of fuel. It also requires fuel to, point it in exactly the right direction. That being said, everything, essentially there was like a maximum weight capacity for the mission, and everything, all of the science instruments, the mirror, everything came in as we expected. So we were able to fill the fuel tanks up to capacity. Launch also went really, really well. So you needed some fuel to make sure that things were on the right course. And it even exceeded the expectations for fuel consumption there. So we actually think, in terms of the fuel, which is really the limiting thing about keeping it in place and pointing it, it's probably at least 20 years worth of fuel on board. Although we're still figuring out, in the first couple of months, how often we're burning through fuel. I think generally speaking, we try to be very conservative with these numbers, but I think, 10 years for sure, I think we're going to get out of it. Now, I don't think it's going to get hit by a comet, but there was pretty early on a small, what we call micrometeorite strike to the telescope. So a very small, I think just a centimeter or so size rock essentially hit the telescope, and we could see it because the telescope shook. We are still figuring out how often that would happen. I think all indications are that is very rare, that specific event, and we were unlucky that it happened early. It didn't affect performance. We don't expect it to, but if a lot of these events happen, then you could expect sort of degraded performance, or you might get very unlucky and it hits the antenna or something like that. But like I said, I think all signs are pointing to 10 to 20 years for sure of science operations at JWST, and we'll revise that estimate as we go along.
Great to hear. We'll expect more lovely images. Some folks are asking about the name of the telescope, various aspects of it. Someone asking, like, why is it called a space telescope as opposed to other kinds of telescopes? And then someone else asking, who is James Webb and why was that name chosen?
Yes. So the space telescope is easy because it's in space. Many telescopes, for example, famous telescopes like the Keck telescopes in Hawaii or the Very Large Telescope in Chile, those are on Earth. And so we just call those telescopes, and things in space like Hubble, we call them space telescopes. All telescopes look at space, but JWST is physically located in space. Now, James Webb, the person, he was the second administrator of NASA. And so he was really very influential in expanding NASA's mission. So NASA at the very beginning had a very narrow focus, geopolitical perhaps, but it was his conception that NASA could also be a scientific agency. So he was really pushing for scientific discoveries, really pushing for development of science missions. And that's kind of what we associate NASA with now, right? So it was really his vision of NASA being a scientific agency that really took over. And so the telescope was named in honor of him.
Interesting. So also perhaps some of this international collaboration, wanting to collaborate more around science missions in the world. Perhaps we see that.
And just to comment about that, it was clear fairly early on that this was so ambitious and so big and so complicated that NASA could not do this alone. And so, it was really very much a collaborative effort with the European Space Agency and the Canadian Space Agency as well. It really took all three of them to get this thing going.
Certainly. There are a couple questions that are coming in that are detailed fine points, and I'll just ask some of those. Someone's asking, could you explain how mid-infrared and near-infrared work in the James Webb Space Telescope?
Yes. So we talk about mid and near and far infrared or ultraviolet. That simply is talking about the wavelength range. So in this diagram that I'm showing you here, it's basically showing you sort of an abbreviated part of the electromagnetic spectrum, with ultraviolet on the left and then further into the radio on the right. So the near infrared is the region of the infrared spectrum that's the closest to the visible part, right? So it's essentially the light that's just beyond what our eyes can see. And as you're moving to longer and longer wavelengths, at some point, it's fairly arbitrary. We start calling that the mid-infrared. And JWST is sensitive to those two parts, right? So beyond what JWST can cover is called the far infrared. And so that's much longer wavelengths. There are other science missions that are dedicated to that, but generally speaking, for the kinds of things that we are most interested in, those major science cases, focusing on the near and the mid-infrared is really kind of what we needed to do. So that's why it was sort of optimized to only go as far out as it did.
Another fine point question here. Can you comment on the impact of the mirror and our understandings of micrometeoroids around L2?
So that was what I was talking about earlier, right? So the mirror was hit by a micrometeorite fairly early on. It didn't break anything. Like I said, it was noticeable. From what I've heard, right, because there were predictions in advance, right? So there are some other telescopes nearby, and there were predictions in advance for how often micrometeorites of certain sizes would hit something as big as JWST. And so, like I said, it was maybe a little surprising that it happened so early on, but at the moment, in terms of the predicted counts of these sorts of events, everything is sort of checking out. So we're not completely overwhelmed by them. We're not expecting JWST to be completely battered by them. I think it was designed to withstand quite a few impacts. And like I said, the sort of operational lifetime of the mission is still sort of 10 to 20 years for sure.
Yes. Also, I realized that we're still kind of at the beginning stages of this telescope, but someone is asking if James Webb has changed anything about how we think about the early beginnings of the universe. If there's been any discoveries that have changed the way that we think about the early universe and its formation.
Yeah. So I'll come back. Sorry, I have these transitions to get through.
Okay.
But it's related to this last point in this last slide that I showed with the spectrum of this distant galaxy. I don't think many of us were really expecting, first of all, how easy this is. I think a real huge compliment to the telescope. I don't think any of us were expecting how easy it would be to see things as distant as we were able to see. So the image with this galaxy that's 13.1 billion years in the past. That was actually not a very deep image. And when I say deep, typically, if you want to see something that's very faint, you have to take a very, very long exposure, right? So those galaxies or those sources of light, whatever they are, aren't emitting a lot of light. So you need to be collecting it for a longer period of time in order to see it. So with Hubble, for example, we have something called the ultra deep field, where we looked at the same very small part of the sky for weeks in order to see the faintest things that we could. This image from JWST is actually just a few hours. So by the standards of kind of the imaging that we expect to do with JWST, it's not very long at all. And we were already able to see things that were extremely distant. So first of all, great job for the telescope. It works really, really well. And then the sort of more subtle point about what's exciting about this and interesting is actually the amount, as I don't have it quantified in the image here, but the amount of oxygen and neon, for example, in this galaxy. Galaxies were actually surprisingly active at forming stars, causing these lines to be very, very bright. So we're still really trying to wrap our heads around these results and understand exactly what's going on. So we think that there have been numerous generations of stars already being born in the first billion years. And those stars also might be producing elements in different ways than stars around us today. So we already have quite a bit to chew on, and we're really just at the beginning.
Another audience member was asking about something they heard about an instrument on the telescope having developed some problem. Do you know what they're talking about? And if you could give any update, if it might impact operations?
So I don't have an update. So that that instrument is called MIRI. That's the mid-infrared instrument. So actually, I could be a little bit more explicit. So the first image that I showed here of the Southern Cross Nebula, this is the near-infrared image. So this is the light that's close to what we can see, but still too far in wavelength for us to see it. The next one, as I said, we're looking further into the infrared. This is the mid-infrared image, and this is from MIRI. So MIRI has a small problem in essentially the mechanism that's used to kind of turn some of the wheels to select certain filters. Without getting too technical, essentially the wheel isn't turning as smoothly as it's supposed to. They're investigating this actively. It's not catastrophic. It's not like the telescope doesn't work. It's only one of the instruments, and the instrument still mostly works. So they're just kind of still figuring things out. And I think that's the other point to highlight, just sort of generally, is we're still figuring out some things about the telescope. And more than anything, we're being very, very conservative, right? So we're learning things about it, and we don't want to push it too hard, too quickly. So, we want to keep the mission going for as long as possible. So we want to be sure about the solution to a problem before we try it.
So there have been a couple questions about who gets to work on this, how many people get to work on this, how the information is shared. Is it all scientists who have worked on this? Is there a public domain aspect to this where people can view information? I wonder if you could speak to that a little bit about who is getting access to this data and who's working on it.
Yeah. So generally speaking, the way that these facilities operate, like Hubble or JWST, is that scientists from around the world submit proposals. They say, I want to use this telescope for this much time to do this science case. And in this case, the Space Telescope Science Institute, so they actually operate the telescope under contract from NASA, they review the proposals. So other scientists, it's peer reviewed, other scientists say that these proposals are the most interesting. We think they're going to be the most impactful. And so we're going to let those scientists use the telescope to do their science. By default, those scientists, once they get their data, they have 1 year where the data just belongs to them. They have 1 year essentially to interpret the results and then, hopefully share the results with the community, write papers, make press releases, that kind of thing. And after 1 year, the data becomes public. You can also always waive that right. You can always say, I want the data to be public immediately. And some things, like all of these images, NASA decided what they were going to look at, so that was also public. So the idea is that, if you have your proposal, that you have some time to work on your science, but also that, in the fairly short term, the data becomes public and anyone can use it, right? Because we really want the most science to come out of this as possible. And given that there is, even if it is 20 years, it is still a limited duration of the mission. We want to get through as much science as we can, as quickly as we can. So more people looking at the data with interesting ideas for science, the better.
Indeed. And speaking of that kind of collaborative scientific venture, I wonder, I've been thinking that JWST is really a great example of international collaboration in science. And I know that you had previously worked for, or as part of the European Space Agency, or on the NIRSpec was part of the European Space Agency, correct? I wonder if you could say more about the international collaboration that made this project happen.
Yeah, so in that particular case, so the NIRSpec instrument was designed and built by the European Space Agency. As I said, the NIRCam was built at the University of Arizona. MIRI was a collaboration between the University of Arizona and a consortium in Europe. And then the fourth instrument is called NIRS, and that was built by the Canadian Space Agency. So each of these scientific, there are teams that build the instruments, but the idea was that they would become sort of publicly used. The science that I'm planning is actually quite a bit with, it's actually a joint collaboration between scientists in the US and scientists in Europe. Again, trying to leverage all of our expertise and also all of our other facilities as well. So for example, we have access to certain ground-based telescopes that are very useful for follow-up observations or, kind of scouting missions to see things in advance of what we want to do with JWST. Some of our collaborators have access to other resources. So yeah, it's a really great example of people working together in the name of science, right? Because otherwise, I think we could be very competitive. There's been in astronomy in particular, there's this historical divide between the US and the rest of the world. And I think those barriers are kind of coming down a little bit with these huge international missions like JWST.
Someone makes a apropos point that we think of it as an international collaboration, but of course it's mainly North America and Europe. Are there any other countries in other parts of the world that are involved with this, or scientists in other parts of the world that are involved with this?
Scientists for sure, right? So even scientists that don't have affiliations with institutes that contributed, right? They can submit proposals to use it. And so just on a personal note, right, I'm working with a bunch of collaborators in Japan on data from JWST, right? So it is meant to be a worldwide collaborative effort, even if it was initiated and led by individuals or agencies from certain countries.
Yes, hopefully we'll see some access. We'll see with other parts of the world. Yes, so there have been lots of great questions, and I apologize that I haven't been able to get to all of them, but I want to just close out here with one last question. Simple one: when will the next set of images be released? What do we have to look forward to? Yeah,
there's not going to be another big sort of press release with 5 images. Actually, it's more than 5, actually. We say 5 images, but there's 2 images of this particular system here. But we're not going to do that. It's going to transition more into like with Hubble, where essentially every time something really interesting happens, a scientist, a group of scientists do something interesting, there'll be a press release. And we've already seen that, actually. There already are a couple of images that I haven't gotten to that are already really widely disseminated from JWST. There's one called the Tarantula Nebula, for example. There's a really great picture of Jupiter as well. So that's really it, right? So once the scientists who have ideas for their projects have kind of done the work and made the images really beautiful, or made the science and the spectra, in a really exciting and digestible way, then those get released through sort of typical media outlets or from NASA itself, right? And so that was the thing that I said at the very end, right? Keep your eye on webtelescope.org, right? They'll keep posting science updates as things come in, as press releases happen. So that's a great way to stay informed, right? Various social media channels, that kind of thing. And then the very last thing to mention is, a lot of the science is happening probably around you, right? So if you're in Wisconsin, people at UW-Madison, like myself and others, we're really actively working on it. So, stay plugged in with whatever your local institution is. And I'm sure they're going to be doing a lot of science with JWST in the near future.
Well, Dr. Maseda, thank you so much. Just like to thank everyone for being here. In a moment, I'll turn it back over to my colleague, Eric Monroe-Kane, to give a closing. But I wanted to just promo one more time the fact that Wisconsin Academy is a nonprofit, and we rely on donations to make talks like this happen. So if you have the ability to give a donation tonight, here is the link. We hope to host more talks on this topic, and we're always hosting different kinds of events that explore life in Wisconsin and new discoveries and scientific research that's happening here in Wisconsin. So we appreciate if you're able to give. And also, if you would like to become a member of Wisconsin Academy, you will receive our magazine, which Wisconsin People and Ideas, which of course discusses Wisconsin people and ideas and provides more depth on issues like this, and also gets you various kinds of discounts to different events. And now that events are starting to happen again out of COVID times, you will have things to take advantage of with a Wisconsin Academy membership. So thank you so much for being here tonight. And Erica?
Thank you so much, Sally-Anna, and thank you so much, Dr. Maseda. It's really been a pleasure to learn alongside all of you tonight. There's so many facts that I wasn't aware of about the James Webb Space Telescope, including so much about the implications of what that technology is making possible. So I just wanted to personally thank Dr. Maseda for joining us this evening, and thank all of you for spending some time with us here at the Wisconsin Academy tonight. And I hope to see you in the future as we have a regular series of science talks as a part of our mission, and as well as many other experiences as have been mentioned earlier on. So thank you so much, and I hope you all have a wonderful evening.